So that's very nonlinear. Okay. So therefore, we're going to typically have to iterate on this. Okay. There's different ways of iterating. There's something called an explicit method, and there's something called an implicit method. Okay. And I'm going to talk about this. So my strategy for the next few slides is going to be this. I'm going to show you kind of what works. And there's some slides on my website where I talk about in more detail why it works. Why it works is going to be related to the Sparrow-Sugonides theory of convergence of finite different schemes that I noted. I don't want to really get into it. I'm going to just kind of point it out that whatever I do kind of satisfies these conditions, in particular the monotonicity condition. Okay. So I've already kind of said this. So I'm just going to go through this one and then through this one. Okay. So I've already kind of said this. So which finite difference approximation do you use is extremely important. Okay. As in, like, if you do it wrong, you're going to get junk. Like you're going to do, your algorithm is going to give you like crazy stuff, like imaginary numbers and stuff, right? Okay. So there isn't like a unique way of doing it, but I'm going to kind of show you what I think is sort of the best way of doing it. Okay. The best way of doing it is something called an upwind scheme. Okay. And I think it's going to be kind of very intuitive. Okay. The rough idea here is going to be we're going to use a forward difference approximation whenever the drift of the state variable is positive. Okay, and we're going to use a backward difference approximation whenever the drift of the state variable is negative. In a nutshell, we're going to use the direction in which the state is moving. Okay, so as in, okay, like here, suppose you're at point I and the state is going up. Right, in this direction, you're going to use this forward difference approximation. Okay, and if you're at point I and the state is going down, you're going to use the backward difference approximation. Okay, this I think is kind of a very intuitive idea if you think about it. Right, it's like Bellman equations are forward-looking things, like optimization problems that you're solving, and so you don't want to use like where you used to be, like you want to use it in the direction where you're going. Right, so that's just kind of the entire idea. Okay. Yeah.
So if the state variable is exogenous variable, I think it's easy to see.
Yes, I'm going to talk about that in a second. Yes, exactly. So now the problem is like obviously with the k, it's endogenous which way it's moving, and so I'm going to show you like a rule for figuring out which way you should move. Basically, the idea is going to be that you want some sort of consistency. I'll tell you in a second. It's sort of a bit of a fixed point if you want. Yeah. Okay. Here's how it works. Okay, this is exactly an answer to your question. So in this example, let's define two ways, and this is exactly what you're saying. So okay, let's do it like this. So ignore this one here first. Let's compute consumption using the forward difference approximation, right? Meaning the inverse of the marginal utility of VIF here means forward difference approximation. VIB means backward difference approximation, right? So let's compute consumption as if we're sure that the forward approximation is the right one to use. Okay, then given consumption, we can also compute savings there. So let's call SIF here savings computed using the forward difference approximation for the value function. Okay, and let's do the same thing here for the backward difference approximation. So SIB is savings computed using the backward difference approximation for the value function. Okay. So then we're going to do the following rule. Okay, forget about this term first. Okay, we're going to use the rule that we're going to approximate the derivative. We're going to use the forward difference approximation if indeed the forward difference approximation tells us to go forward. Okay, we're going to use the backward difference approximation if indeed the backward difference approximation tells us to go backward. So it's kind of internally consistent, right? It's like then everything is kind of correct. Like what you wouldn't want, right, is that so this is why there's a third term and there could be a fourth term. Let's talk about that in a second. So what you wouldn't want is like so then sorry, let me say this slightly differently. So so you can see this is not necessarily exhaustive, right? So it could be that in particular that the savings computed using the forward difference approximation tells you to go backwards, right? But savings computed using the backward difference approximation tells you to go forward. That would be one case. Okay. What do you do then? You assume that you stay put. Okay. So the assumption is basically you're kind of at the steady state. Okay. In particular, then at the steady state, I'm going to use this thing here, which is that I know that the value function at the steady state is, so you always have a first order condition like v prime of k equals u prime of c. Then staying put means that consumption, you just eat your income, so that k dot equals 0. So that's what you have. Okay. There's one more case, which is probably your question, which is there could be another case too, right? Which would be, which way does it go? So the backward, so the forward, I'm gonna screw it up. Okay, anyway, obviously there's another case, okay?
What if both of them are true?
Yes, exactly, sorry, that's the case, thank you. Okay, exactly. And you can see it's not there, okay? And the reason it's not there is that actually in this kind of problem it can never happen, okay? Here's the reason. It comes from the value function being concave, okay? So here what you can see from here is as long as the value function is concave, you're going to have that the forward difference approximation is always smaller than the backward difference approximation. Therefore, this is, so minus u prime is a decreasing function, minus u prime is an increasing function. Therefore, this is always smaller than this one. Okay, so you're not going to have that case. Okay, okay. For non, you can also have non-concave problems. Then you're going to have a more complicated thing, but you can take care of that. Okay, there's some the problem with the non-convexity, like the Skiba thing I mentioned in the introduction, is going to have that feature. Then you are going to have to do something slightly fancier, but it's basically the same. Yeah.
Unexpected central difference will show up in the third term.
Nope. No, because in the third time, because
you just show the central.
Yeah. I was sort of debating whether I should put that slide there with the central. I mean, so okay. So the answer is just that. I think it may actually be the case that you would get something sensible with the central. Okay. So here's the answer. This way of doing it is one way of doing it, which satisfies these Barthes-Tsouganides conditions. Okay. There's a possibility. There's another way of doing it, which has the central. I'm not sure.
Figure out that it doesn't work, or
I don't know. You can do that. The one thing I would say is we're typically going to take such a fine state space. Like we're just going to have like 500 or 1,000 grid points. It doesn't matter. Okay. It's not like it's not like it matters that this is a better approximation than this one, because once you make the grid space fine enough, that's it. Okay. And so this is what I just said. So you can't have, so you can't have that case. Okay. So here's another way of looking at this, and this is going to be to show you the sparsity that I talked about. Okay. So if you look at this equation here, and now use this rule that I just told you, there's another way of writing it. Okay. Just without the vi prime in there. Okay. Which is like this. Okay. Let's write it like, so these terms are the same. Okay. Then I took the derivative term here, and I made it such that, so I'm sorry, I should say, I'm going to use the notation that something with a plus superscript means like the positive part of that, okay? And something with a minus superscript means like the negative part of that, okay? So this is either positive or 0, this is either negative or 0, okay? So this then says, so this is basically just another way of writing this indicator thing, okay? This says that if savings are positive, then you use the forward difference approximation. If savings are negative, then you use the backward difference approximation. They can't be both true. Okay, so it's either this one is switched on or this one is switched on, or none of them. In which case, you just you're at the steady state. That's what you said. Okay, so if you look at this, and this is kind of going to be important. You can it's comma I equals 1 to capital I. Okay, so there's capital I equations of those. Okay, say like 1,000 grid points, you have 1,000 equations. You can write this whole thing, the system, in matrix notation. Okay, and it's kind of gonna look like this. Okay, where V is a vector in which I'm just like putting all the VI's. Okay, then U is a vector where I'm putting all the U of Ci's, okay? And then to capture this thing here, I can always write it as A times V, some matrix, okay? Where A is of dimension capital I times capital I, where capital I is say 1,000, sorry. So the number of grid points. And the key thing now is this matrix looks like this, okay? So what is this? So there's a very cool function in MATLAB, it's called SPI, okay? The function SPI, it takes a sparse matrix, okay, and gives you a graph like that. And the graph, what the graph does, it has white everywhere where there's zeros, and it has blue wherever there's non-zeros, okay? So here I just took one example with 70 times 70, so you can see stuff. Typically you would have more grid points. And what you can see here is already that it has this kind of tri-diagonal structure. Okay, so there's a diagonal, which is kind of here, which is non-zero for most points except here. Okay, and here there's some things above the diagonal. Okay, and here there's some things below the diagonal. Okay, but there's never like a non-zero here or like there or whatever. Okay, so now, okay, how do you go from here to something like this? So the way to think about it, okay, is right. I just took the term, this term, right? You can always take this term for a given row and write it like that, okay? And then you can stack that whole thing in a matrix. And you're going to have a matrix that's going to have a diagonal with these terms and off diagonals with this terms, okay? Yeah.
Is S a function of V?
Yeah. So I'm going to come to, yes, exactly. I'll come back to that, yes.
So the break is suspected, like
What?
the break, like where it's like white is the suspected steady state.
It's just the steady state, yes. Yeah, exactly. Oh, I see. Yeah, it's exactly. It's yeah. Once it's converged, it's the correct steady state. For a given guess, it's the sort of suspected steady state. That's right. Exactly. So that was my next question to test whether you're paying attention, which is exactly what's this thing here? That's the steady state, right? Because there's zero. So okay, what is this matrix? This matrix is kind of like the transition matrix of how the process moves in the state space. Okay. And the point is, like, if there's zeros, it means you're not moving. Okay, where you're not moving at steady state. Okay, so then how to read this is if the matrix above the diagonal are non-zero, it means you're moving up. Okay, if the entries below the diagonals are non-zero, it means you're moving down. Okay, in particular, I think one can actually be a bit more precise. If you stare at this, okay, you can actually show that all the diagonals are always negative, okay, and all the diagonals are always positive, okay, and the intuition that this is kind of an outflow of the diagonals, and you either go to the right, then an inflow here, or you go to the left, okay. So the point is this matrix here captures this. So why do you go to the right here? You're below the steady state, so you go up. Here it's like you're above the steady state, you go down. In this particular model, which is globally stable, this is what it's going to look like. Okay. One other comment is, so this I've already said, the matrix always has the feature by construction that you have sort of negative diagonals and positive up diagonals. The other thing that happens is the rows sum to zero. Okay. Why is that? It's like, because it's a transition matrix. Okay, if you use the discrete time transition matrices, what's the feature of the matrix? It's the rows sum to 1, right? Here, because it's continuous time, the rows sum to 0. Okay, as a general rule, anything that's a 1 in discrete time is a 0 in continuous time. Okay, like, I think it's actually true. Okay, I'll show you some more examples of this rule later. Okay, so that's how it works. Okay. Okay, is that kind of clear? Okay, now is what you said. I cheated a bit on the previous slide. So in particular, the matrix A and also this U thing, because it had consumption in it, actually depends on V. So it's a nonlinear problem. Okay, that's what I said before. So you can't. So if it were just this, you could actually solve it in one go, right? You just bring it over to the other side, invert that. If it's not like that, so you have to solve it non-linearly. Okay. So next, I'm going to show you how to solve it non-linearly. Okay. So it was a pedagogical cheat. Okay. So here's how to solve this. I'm going to first show you one particular way of solving it, which is called of iterating, which is called an explicit method. There's not going to be any matrices in there, actually, you're going to see. And then I'm going to show you an implicit method. Okay. Just to be clear, the explicit method here is mostly for pedagogical reasons because it's easier to explain. In general, you don't want to do the explicit method. Okay, you want to do implicit method, which is going to be on the next slide. Okay, so here's the idea. So the idea is you solve the first order. So okay, no. So the way we're going to do it is right. We're going to guess some initial value function, and then we're going to iterate on it. Okay. So now let's guess. So suppose you guess some initial v, I0. So a good guess typically is like staying put at every grid point, right? So it would be u of f of ki minus delta ki over rho, like if you always just stay there. So what we're going to do is we're going to basically, given a guess for the value function today, we're going to solve the first order condition, and then we're going to update the value function according to this rule. So in particular, we're going to compute the finite difference approximation using the rules I showed you. Sorry, this should probably say a few slides ago, not the previous slide. And then we're going to iterate on this according to this rule. So we're going to find the value function at the next iteration using this thing. Okay, right. So this is the current value function vin, and then vin plus 1 we're going to find using this thing. Two things. So the first thing is everything kind of looks the same as before, except there's this weird thing here, right? So what's that? So this is just an updating rule. Okay. So you can see if vin plus 1 equals vin, then which is if it's converged, then this drops. And so if it's converged, you know that it satisfies the equation. Okay. The other thing, and I'll come back to this, is what you can actually see is like here you can actually do the updating point by point. Okay. So you can you never have to write anything in matrix form. In particular, given an initial vector, I just point by point I can update that thing. Okay, and in particular, so you can find vin plus 1 at each point explicitly as a function of vin. That's why it's called an explicit method. Okay, there's a problem with this explicit method, which is there's this important parameter here called delta. Okay, that's here, which is sort of the updating step size. So you can see if you kind of rearrange it so that vin plus 1 is just on the left hand side and all the stuff with n's on it is on the right hand side, everything is going to be multiplied by delta, right? So it's like if delta is small, you're updating slowly, and if delta is large, you're updating quickly. And it's going to turn out that you basically, and this is sort of a general thing about these explicit schemes, you cannot choose the step size too large. Okay, there's something called the Courant-Friedrichs-Levy condition. So it's like the Courant after the Courant Institute Courant guy. That kind of proves that for general finite difference methods that you cannot be too large. Okay, so as a result, you can kind of go slowly, and it's pretty inefficient. So for example, I need like almost 6,000 iterations in the code that's on my website, but it's still pretty fast. It's still only like half a second or something. But I mean, it seems a bit awkward to use like 6,000 iterations. Yes.
So this delta is very different from delta k, completely different.
Yes, absolutely. Sorry, I should have said that. There is an interesting thing, which is that this CFL condition here actually shows that the delta here, the step size you can take, is actually kind of bounded above by something proportional to the delta k, which just kind of makes it extra bad, because like it means that if you want a fine grid, you can only update very slowly. Okay, that's really why the killer for this thing. Just because you asked, if you look at this, and this is something that may be helpful or not. Let's see. If you look at this, it kind of looks like a time derivative. Okay, if you've ever seen time-dependent HAB equations, except it's like on the wrong side. Okay, and in fact, it's like sort of there's a minus in front. And the reason it's kind of like, you can think about it also as like you're reversing time. So it's like you're solving backwards from a terminal condition until you find a stationary solution. But that's okay. That's just a throwaway that you can kind of forget if you didn't understand that. Okay. Okay. So I told you this is kind of bad. You don't want to do that. Okay. But it's just to explain. Okay. Here's the good way of doing it, which is what's called an implicit method. So why is it called an implicit method? Is because now we can no longer find the VIN plus 1s explicitly. In particular, the way I'm going to do it is I'm going to just put n plus 1s on a bunch of things that didn't have n plus 1s before, that had n's. Okay, these things here. Okay, what you can see then is you can no longer find the VIN plus 1s explicitly. Instead, you're going to have to solve a linear system. Okay, at each step, you're going to solve a linear system which looks like this. Okay, so you have a Vn plus 1 here because there's a Vn plus 1 here, and then also 1 here. Okay, so now you can write this in matrix notation, and you're going to have this matrix show up here from before. Okay, so how do you do this? So you just do the normal thing you do when you have a linear system. You just kind of bring all the things with n plus 1s over to this side. Okay, and then you're going to invert this matrix, and you have the solution. Okay. Now the nice thing, so you may think, oh my god, now at each iteration I'm going to have to invert a matrix, okay, and that's going to be super costly. But the answer is it's not. In particular, this matrix is very sparse, okay, and MATLAB is like amazing at solving sparse matrices, and you can check this out, and it's super fast. Yeah.
I thought the V prime is going to be translated into S, and the S is A.
Yes, that's right.
So I thought A contained Vn plus 1, but here A Vn.
Yeah, but it's here because I put a, sorry, I'm using Vi prime for Vi prime n for consumption, and consumption then this is the S, right?
So the Vn plus 1 prime, I thought that part is actually in the A. It's not.
Yeah, no, because the V n plus 1 prime gives you this thing, right? That's this thing here. Because right? So the point is, you take this thing, that's Vi. So these things now have n plus 1s on them, right? Now if you write this in vector notation, that's like n plus 1, n plus 1, n plus 1 times that. Exactly. So here the idea would be, this things has n's on them, and this things have n plus 1s on them. So then the A has n's, and the right, that's exactly so. Yeah? Okay. And you can also again see, like, once this thing has converged, you get back that thing, right? Okay. Now, just one thing, and then we'll have a short break. And just kind of good to know. So how do you actually do this? So you can go to the website. There's one important sort of consideration, which is, if you want to do this in MATLAB or any software package, and you want to take advantage of the speed gains of these matrices being sparse, you have to tell MATLAB or any software package explicitly that the matrix is sparse, right? Because, I mean, how would the software package know otherwise, right? In particular, the code you will see gonna has some parts that looks like this. So whatever is mu here is S from before, so maybe SB, SF, okay, and so on. And so the code has a thing like this, and so I used to write my code like this, okay. So you have some vector x, some vector y, some vector z, which has these are these things here, okay. And then I have had a loop, okay, which said, okay, let's construct the n by n matrix, I by I matrix, I guess here, which puts like, stuff on the diagonals, and one to the left and one to the right. Okay. Then I had a very good student who told me, this is the most stupid code I've ever seen, and he's right. Okay. And he's like, what you should be doing instead is this. Okay. Which is, MATLAB has these like sparse matrix syntax, and it basically says make a matrix A that has the vector y on the diagonal, the vector x one to the left of the diagonal, so -1, and the vector z one to the right of the diagonal. And you can see A, it's one line of code, and B, it's much faster, and C, it already tells MATLAB it's sparse. Okay, if you really wanted those stupid loop code, you could actually do that, but then at least you have to write afterwards, you have to write one line, which is A equals sparse A, okay? Meaning you tell MATLAB it's sparse. Otherwise, this whole thing, meaning like that it's fast, is not going to work. Okay, let's take a little break, but literally 5 minutes, otherwise we're going to run out of time, and you can ask some questions if you want, and so on. Yeah.
So this one, what I meant is that you can take derivative with respect to k. Then you get vk.
I mean, I understand, but then
right. Then you can
what?
solve the c equal k. Because this is going to be fk plus 1 minus delta. So you can get the c equal something.
Okay, I actually never thought about that.
So
and then what? But does that actually work?
I don't know, but I thought that your point is that...
yeah, but I don't think that would work. And then you would plug that in here?
Right.
Yeah, but okay, to try it, I bet that doesn't work. Like I'm saying, like as a practical point that you
But you will get the same thing. Then vk, the right side is going to be uck. No, I thought... I'm not against the method. I'm just saying...
No, but I'm just saying, like... I'm saying if you... Okay, here's something you could do, which I think you're saying, right? So you could here's a problem. You could say, let's solve this problem rather than taking the first order condition.
No, this is equivalent to taking first order condition. Because this uses the envelope theorem.
Yeah, but it's not... But I'm just saying, like... okay, here's what I'm saying. Take this problem, and I want to know the value function at the end. Compute it.
Right.
My claim is... So what you seem to want to do is get rid of the max here and substitute
so this
that.
Is envelope theorem.
Yeah. And you're saying like substitute that, the consumption from here into there.
Exactly. Then
and my claim is this: if you try to solve that code, it's not going to work. Like no way.
Conceptually, they're the same level.
Well, I don't know. But I challenge you to try to code it up. I don't see that working because you're not taking the first order condition.
No,
but just try it. Okay. I'd be very impressed if this works. Please send it to me. That would be great.
My claim is that when you say this is unique to, I guess yesterday someone asked the same question. You said this is
the condition.
Right.
No, I never made the claim that the condition is unique to discrete time.
In time, you can have this, so it's convenient. That's what
but it's convenient because you can use it in the computation.
Oh, that's your claim.
Yeah.
Oh, okay. So
no. There was never a claim that the condition is unique. Yeah, whatever. I don't care. That's totally fine.
Because there's no sparsity or something? Is that your claim?
No, I'm just saying if you try to use the envelope condition instead of the first order condition here, it's just not going to work. I mean, try it. I mean, I've never tried this. Maybe it would be really interesting if it were to work, but I'd be very surprised.
I understand you. Okay, thanks.
I want to ask about the HAB. So, let's say I have a well-defined problem, like a sequence problem, like in continuous time. So, how do I do you have any references that I can look into that okay, so this is in this HAB is indeed the problem, solution of this HAB correspond to the solution of their
sequence problem,
and that their solution to HAB is unique and it satisfies the smoothness, smooth passing and whatever.
Yeah, I can give you a reference. But no, there's no smooth pacing here, right?
Yeah, I mean, but then most of the time, if you look into any Ito problem, Brownian states, then it should be some smooth pacing.
No. That's only if you have stopping time problems.
But
so
I have stopping.
So okay, but so the key theorem is, and these are there's three theorems. Okay, these are exactly what. Okay, theorem one. It's always under some conditions, but okay. An HAB equation has a unique viscosity solution. Okay. Theorem 2, unique viscosity solution equals value function from sequence problem. Okay. Okay. Theorem 3. The finite difference method converges if you do it correctly, if you do these, satisfy these Ball-Sigonides conditions. Finite difference method converges to the unique viscosity solution. Then that's everything you want, right?
So uniqueness, existence, uniqueness, and
So this is not, but this is exist. Sorry. This is exist. 1 second. This is both existence and uniqueness. This is just an equivalence between the solution. No, the sequence for me here is just the sequence problem here would just be like. If you, okay, let's do that. Like, what he means by sequence problem is just this, right? The problem like that's like this. And you'd want to know that, right? You'd want to know that when you solve this HAB equation, you actually get that thing, rather than, I don't know, some other V. Yeah, that's all I said.
I have 2 questions.
Okay.
Really quick.
Sure.
So number 1 is, are you always going to use an equally spaced grid for the state?
No, you can do a non-equally spaced very easily. In fact, like, so there's some applications where, so in this case it doesn't matter because additional grid points are very cheap because it's just a one-dimensional thing. But if you have, say, 3-dimensional problem, then grid points become more and more expensive. Therefore, typically, yeah, you want to kind of economize on the grid points. So you want to maybe only use 100 instead of 1,000, and then you would want to put more grid points where there's curvature in the value function. So say close to the boring constraint, and you can do everything. I mean, it's just that, okay, then it's like this, right? Vi, so V prime of Ki would be, for example, Vi plus 1 minus Vi over Ki plus 1 minus Ki.
Yeah, it's just that you went a bit fast over those conditions that guarantee that you actually converge the solution. I was wondering if some things related to how you choose your grid, or if it's just the structure of how you define these differences.
Yes. Yeah. So like, yeah, it doesn't matter. Any way of choosing the grid is fine. Yeah.
So where should I look up for the theorems?
In my slides on my website, let's see. Do I have internet here? Here, there's a lecture notes on viscosity solutions. There's all the references. The good one is this book by Barty, or if you want the rigorous stuff, then go to Barty and Capuzzo Dolcetta, for example. But so here, I'm stating this somewhere.
Do you have the theorems here? Like, I mean, just need to check the conditions, right?
Yeah, but it's.
Everyone agrees.
Yeah, I don't know. I don't have it here, but I mean, it's like. I mean, it's like anytime you think you have a unique sequence problem. For example, if the problem has like a convex or concave objective function and convex constraint set.
I understand.
You're gonna have.
I still need to like write those, like check those theorems too.
Yeah, I mean, you have to go to those books.
Thanks for
Just one question, sorry.
Okay.
We're interested in about this numerical stuff,
Uh-huh.
and I thought the first thing, if I'm the first one who have to do this, I'll remove this and put this Vn and just have Mvn plus 1. That seems to be the simplest one and the analogy of the discrete time. And what does that work, and why don't you choose that simpler one?
I don't know if it works.
Maybe there are some.
Yeah, I don't know if it works.
I just
We
wanted
can try.
to know if
Yeah, but I don't. I mean, I think this is equally simple.
No, the thing is, this thing I couldn't come up with when I first see the problem.
Oh, I see.
Right. So if I have to do it, I will do Vn and
Okay.
just the
But what definitely works, what does definitely work, is if you get rid of this so you set delta equals infinity. As long as you have the n plus 1s here and here, it's going to work. So you can get rid of this.
So it seems this is really the tricky thing. Makes the name implicit, right?
Yeah.
So it
Yes.
seems this is the key.
Yes.
That makes it work.
Yes.
And
I do think you want to put the n. I don't know. I don't know. I don't have a good intuition. I don't know.
Yeah. The trick is there. Okay.
Yes. Yeah. Okay. Let's continue, guys. Okay. One more half hour. So this is just going to be. So okay. First, are there any questions on what we did so far? Did this kind of make sense? So I mean, the goal here, right, is that you can go to my website and like look at this kind of code, and so you can run it, but then also that you kind of sort of understand what's in the code. Okay. So I think that, I mean, as long as I achieve that, I'm a happy man. Okay. So let's briefly do problems with non-convexities. Okay. Here's a problem I kind of like, and I'm going to show you that this is a problem where I would argue it's hard to solve it in discrete time, and it's going to be very easy to solve it in continuous time. Okay. So let's do the same neoclassical growth model from before, but let's drop the assumption that f is strictly concave. Okay. Instead, I'm going to use what some people call a butterfly technology. Okay, I'll tell you why in a second. Okay. Here's the idea. Okay. Suppose like the country or whatever, you can think about this as entrepreneurs or something like that. Suppose the country has access to two technologies. Okay, a crappy technology, F low, and a good technology, FH. Okay, the difference is that so the crappy technology, it just has a low productivity. Okay, so AL is less than AH, and the good technology has a high productivity, but it kind of has a per period fixed cost. Okay, so each time you want to switch on the machines, you have to first burn some capital. I don't know. You have to switch on the lights, and I mean, there's some fixed cost in production. Okay, you can do this more fancy in terms of labor, but this is kind of good. Okay, so then what I'm plotting here, right, is the two production functions. So this is the bad production function as a function of capital, this one, and this would be the good production function, right? So first you have to burn 2 units here of capital, and then you get a good production function. Okay. Then the effective production function is not hard to see. It's like the upper envelope of those things. Okay. So this is also why it's called a butterfly. Okay, because this is like a butterfly, right? I don't know. For creative people. Okay. So if you ever try to solve, and I should say, there's lots of problems that are like this. Okay. There's problems with occupational choice that are like this. Problems, and there's one in my paper from Tuesday. If you have, say, you're doing consumption saving problem with housing, and housing is indivisible, and there's collateral constraints, you're going to have a non-convexity like that. Okay. Yeah. I mean, yeah. So I mean, it's easy to come up with problems like this, and in fact, like many interesting problems are like this. Okay. Why? So why are these problems interesting? This problem is kind of interesting because it can generate kind of poverty trap type dynamics, right? What's typically going to happen is, and I'll show you this in a second, is there's going to be some sort of a threshold point, such that like if you were, so say some threshold capital stock, some threshold initial capital stock, such that if you're below that, you're going to be stuck in poverty forever, and it's got stuck with the shitty production function forever. And if you're just above that, then you start using the good production function. One interesting thing to think about is, so okay, here's one thing you could have thought, right, which is this threshold that I just talked about for where the poverty trap is exactly this point here, where the two technologies cross. I'm going to tell you that's not true, okay? Instead, it's going to be somewhere else. You can think about where it's going to be, okay? Okay. So if you solve this in discrete time, you're going to have a problem, okay? What's the problem? The problem is that the first order condition, so in discrete time would be something like this, is no longer sufficient. So it's still necessary, but no longer sufficient. So you're going to have typically multiple solutions. Okay, in particular, right, what's going to happen is that typically the value function is going to have a kink. Okay, therefore the derivative kind of jumps. And therefore, this equation can have multiple solutions. And then, you have to, you can't use first order conditions anymore. So you have to do the brute force thing, or you have to take the two, say, solutions of the first order condition, and then after the fact, look for the one that's globally optimal. I don't know, some weird stuff, okay? And the problem is kind of like you have to worry about crossing the non-convexity between today and tomorrow, okay? For some, right, like you kind of here, you have to worry about like going here and then the value, okay. Or you can do it in continuous time. For some people who've maybe seen this before, there's an old literature that does this kind of problem, deterministic. It only works for deterministic problem. But you can do this with like phase diagrams. So this is from this Skiba paper, who is some Russian mathematician, I think. And you get these phase diagrams with these cool cycles. But okay. So you could argue that you get some intrinsic utility out of a phase diagram like that. So what I want to show you is sort of, unless you get very high intrinsic utility, you don't want to do that. Okay, I'm going to show you the simpler way of doing it. Okay, so you can get these kind of cycles, and so this is exactly those two steady states. Okay, with a poverty trap. Blah blah blah. Okay, so here's the point. The point is, you can solve this problem here using a finite difference method, and in fact you can use it solving exactly the same finite difference method that I just showed you. You basically use exactly the same algorithm as for the growth model with a concave production function, and it works. Okay. There's one thing I should say, which is that if you remember this thing that we talked about, which is that I said because of the value function is concave, you can kind of ignore that case where like both the backward drift and the forward drift, they kind of go in this they both are kind of consistent with going that direction, and you can ignore it. Here you have to like adjust it a little bit to take care of that, but that's kind of easy, okay? But other than that, you can do the exact same algorithm. In particular, you end up with this sparse linear system that you have to solve at each iteration, okay? And you actually get some really interesting stuff out of this, and this is kind of the stuff you can get out of this, okay? So this is a typical savings policy function you're going to get out of this, okay, for example. So this is capital here. This is savings here, so k dot. So meaning that if k dot is positive, you're accumulating. If k dot is negative, you're decumulating. So the first thing you get is two steady states, right? So where do you see two steady states? There's two steady states here. There is one. Steady states are always where these policy functions intersect zero, right? There's one steady state here, one steady state here, okay? And then the other interesting thing is that you have this like critical point here where, so I forget whether it's, I think actually the policy function is just discontinuous. I forget. Either it's discontinuous or very steep, one of the two. I think it's just discontinuous, where the policy function goes from negative to positive, okay? So what's this point? So this point is where the poverty trap threshold is, right? So like if you're just to the left, you're gonna like be stuck with the crappy technology and sort of linger in poverty forever. And if you're just to the right, then you're gonna end up with a good state. Now, one thing that's interesting, and this kind of a general feature of these kind of problems, is, and I kind of tried to get you to think about this before. So the black dot here is the same point at which those things cross. Okay, so you can see actually the poverty trap threshold is sort of below that point, right? This point is below that point. So why is that? Kind of makes intuitive sense, right? If you're just below that, what you want to do is you want to save up, and so that you have enough capital so you can use it, and then you go to the good steady state. So this is a general thing. These points that they're called kind of Skiba points. Okay, the Skiba points will be generally below where the non-convexity is in the production. Okay, but if you're just below the Skiba point, then here, if you're just above the Skiba point, you're gonna sort of think like, oh, okay, cool. I'm gonna save up until I can use the good production function, which starts here then. And if you're just below, you're like, I'm not gonna bother. It's too costly, so I'm just gonna go with it there. Yeah.
So you mentioned that in discrete time, the first order condition is not sufficient. Continuous time may be sufficient.
Yeah. And the reason is, okay, you can look at this. So I'm going to tell you something, and then you're going to agree with me, but you're going to say, like, but isn't there another problem? But let me just, okay. So you can see that the first order condition here is u prime of c equals v prime of k. Okay, in particular, there's no k prime in there. And so v prime of k is just a number. So therefore, there's just a unique solution to the first order condition. And that's it. Okay. Now the thing you're probably going to say is like, and that's actually true, which is, isn't it going to be the case that this value function is going to have a kink? Okay. Hence, if it has a kink, what does it actually mean, v prime of k? Okay. And that's a good question. So, and the answer to it is, that you can actually have solutions to differential equations like this that are not differentiable everywhere. Okay. In particular, this is exactly this whole viscosity solution thing. A viscosity solution is exactly a solution to a differential equation that to a Hamilton-Jacobi-Bellman equation, sorry, that allows for kinks at various points. Okay, you can only have particular kinks. Okay, so it's like turns out you can only have like convex kinks, not concave kinks. Okay, but you can have kinks. Okay, in general, there's a sort of a, so the whole apparatus of this viscosity solution is actually kind of designed to handle problems with kinks. Okay, even though you may think, okay, what does it mean? Okay, and this is sort of a general thing. If you have partial differential equations, there's often something called a weak solution to a partial differential equation rather than so the normal thing is a classical solution, right? The classical solution is a solution that has as many derivatives as it needs to hold for this equation to hold. So a classical solution would be one that's everywhere continuously differentiable. For many problems, you cannot find classical solutions, but you can find weak solutions. And the viscosity solution is a particular weak solution. Okay. Okay. That's kind of it. And so, what does this A matrix look like here? And you can kind of think about this as the SPI function again, which puts zeros everywhere, white everywhere there's zeros and non-zeros here. So here's how it works, right? So now you have two steady states, one here, one here. Okay, you can see here you're going up. So you have entries to the right of the diagonal. Here you're going down. So that steady state is stable. This is just consistent with that policy function, right? And here you're going up, so you're going toward the good steady state, and here you're going down, so you're also going toward the good steady state. Exactly consistent with that part of the policy function. Yeah.
Does this mean the sharp increase is actually discontinuous?
Yeah, exactly. You can kind of see it here, right? This switches exactly. That's right. Yeah. Thanks. Okay, that's it. Any other questions on? And this again works for problems with non-convexities, like any problems with not any, but a lot of problems with non-convexities, as long as they're not stopping time problems, which is like what we'll talk about tomorrow. Okay, but problems with occupational choice will typically look like this. Okay.
So Ben, does it change does it solving for a viscosity solution with a kink? Do you start with a specific case, or you start with any case you want, and then just the problem takes care of it itself?
Yeah, exactly. So you can start with. So the only thing you want in this case is you want to start with an initial guess that's increasing. Okay, just because you're gonna have like b primes showing up, and you don't want that to be 0 because otherwise you have like consumption is 0 to some negative power, and that's obviously not good. But as long as exactly. So this is actually kind of the point. Thank you. It's like just take any initial guess that's an increasing function. Okay, the theorem basically says the algorithm is going to converge to a unique viscosity solution. In particular, it's going to kind of just find these multiple steady states itself and like this kind of Skiba point itself. So exactly, you don't have to guess where it is or do any of this kind of weird stuff. Okay. So one thing, actually, I'm just remembering one thing I should have also said in the neoclassical growth model. So another thing you may have noticed, maybe, is that I never discussed any boundary conditions. Okay, and this comes back to this thing that I said before, which is you don't want to think about it as ODEs that require boundary conditions. Okay, so here's how it works. So usually you would put like a boundary condition here, right, or like here at k min or k max. So I don't do that. Why do I not do that? If you think about it, it's because I have this upwind scheme, right, that tells me like on the bottom where I go up, just use the forward difference approximation. So you only use information looking inwards on the state space, and the same on the top. I mean, they're symmetric. So you never use the grid points like, say if this is grid point 1, you never use grid point 0 like off the grid, or you never use grid point capital I plus 1. Right? You just always use inward looking information. Okay? So the algorithm kind of solves this differential equation without using boundary condition. Okay? If you want, there's a slightly other way of thinking about it. It's like sort of the algorithm finds its own boundary conditions, which are, I guess, the steady states. Okay? But I mean, okay. So it's kind of cool because you don't never have to worry about boundary conditions. Whereas if you did the Math 101 thing and went to the MATLAB ODE solvers, then if you can't think of a boundary condition, you're kind of screwed. Okay? Because it just like the function asks for a boundary condition, right? So like if you can't provide it. Okay. Any questions on this? Okay. So now let's do the problem we actually want to solve, which are these heterogeneous agent models. And the point is going to be very easy. Okay? So here's the key idea. So now the heterogeneous agent models, if you remember from the talk on Tuesday, I'm going to write it in a second again, would tend to be a coupled system of Hamilton-Jacobi-Bellman and Kolmogorov-Ford equations. Okay? Turns out that the Hamilton-Jacobi-Bellman equations are kind of sort of hard, or I don't know what you want to call it, relatively hard to solve, but I kind of just explained to you how to do that. Okay? So it's going to be